First melts question. What is Kirchhoff's current law at node 1? So get on the melts, it should be already open. What is Kirchhoff's current law at node 1? Revision from the last lecture. And not active. What's it say? No active questions. Alright, let me try this. What about now? Now. It's magic, isn't it? It works. All right, it's open now. Do you want to just email me and I'll find out why you're not on the list. Yep. Just email me. I'll find out why. Possibly. Quite possibly. Put either then. All right, 70 responses. $80 responses, it's pretty good. We'll see if we can get to 100. All right, there's 100. So, and the answer seems to be very split between I1 plus I2 minus I5 equals 0 and minus I1 minus I2 plus I5 equals 0. Well, they're exactly the same thing, so either B or C would in fact be entirely correct. So let's remember, we sum the currents exiting or entering, whichever one you want. So that current is I1. Got to add that current, which is minus I5, and I have to add that current, which is I2. It's that, or it's the negative of everything. It's the same idea. Well, what about at node 2? Let's say the current's entering here. That one is I2. That one is plus 50 I2. And then this one is minus I3 equals 0. So I've done some of the currents exiting on node 1, some of the currents entering on node 2. Both of them must sum to 0. Any questions about that? Should be nothing new, just some revision from last Monday. Quiet please. Bit of shush, 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 shush. All right, then we said, what's a loop? It starts at a node, goes through some other nodes and comes back to the first node again, the starting node, but doesn't go through any other node twice. So in this one, there are only 3 nodes. 1, 2, and 3. So a loop might start up here, go there, and go there. That would be going from node 1 to node 2 to node 3 and back to node 1, which is fine. That's a loop. we saw some nice examples at the end of Monday's lecture that were not loops. If you don't start and finish in the same place, or you go through any node twice, then it would not be a loop. Today we're going to sum voltages around loops. That's the significance of loops. Sum voltages around loops rather than summing currents entering or leaving nodes. That's going to give us Kirchhoff's voltage law. But I do need one person for another student. Oh, you, yeah, again. Yeah, that's why you're ready to go. All right, okay. What I want you to do, I want you to run up to the back. And I want you to come down again. Yeah, very good, very good. And then run up the back again. Or do you think once it gets the idea? All right, okay. Now run out. No, it's all right. You can stay. On the way up, potential energy increasing. On the way down, potential energy decreasing. The sum of the potential energy gains around that loop must be 0. And that's all that Kirchhoff's voltage law is in fact going to tell us. Excellently demonstrated. Would you like a coffee voucher or a book on engineering design? What? You can have the book on engineering design, yeah. I would have gone for the coffee voucher myself. It's a rubbish book. That's why I'm giving it away. But anyway, no, it's pretty good. I just got a new edition, so I give away the old editions when I get new editions. So very, very well demonstrated. I sum the voltage drops across elements around a loop, and that sum must be 0. But as I go around this loop in this direction, I can say V1 plus V2 plus V3 plus V4 equals 0. But notice what's consistent is there's a positive terminal first, positive first, positive first, and positive first. So the reference direction has to be consistent. So when we go around loops and we encounter first the positive and then the negative, I'm going to write plus voltage. If I hit the negative first, going around the loop, I'm going to write minus voltage, minus the voltage drop. You could do either, but you have to be consistent around the loop. Now that's very much like the fact we could have summed the currents entering, or we could have summed the currents exiting, either one, but at a particular node you have to make up your mind and be consistent. The same going around the loop. We're going to sum the voltage drops, if you like. Hit plus minus, I'll write plus. So in this case here, going around the loop in this direction, I said V1 plus V2 plus V3 plus V4 equals 0. And essentially, you can think of it as a conservation of energy result. So let's consider this circuit. It says, I know VR1 and VR2. If I do, tell me what VR3 is, the voltage on the resistor down on the bottom. I'm going to start at this A, and I'm going to go around a loop in this direction until I get back up there. So starting at A, my first voltage drop is VR1. I encountered the positive first, so I write positive VR1. I then get along and I'm at this, what am I going to write? Minus 5. Beautiful. I hit the negative sign first. That's in fact a gain in energy. I'm going to write negative 5. And then I come to the resistor R2, this thing here, and I write plus VR2. Then I'm at the 15 volt source, but I hit the negative first, so I write minus 15. Then I'm at resistor 3, plus first, so it's plus VR3, minus 30 equals 0. That's it. That's Kirchhoff's voltage law around the loop. The question said, if I know VR1 and I know VR2, what is this one here, VR3? So I'll say, well, VR3 must be equal to 50 minus VR1 minus VR2, whatever VR1 and VR2 happen to be. So we don't yet worry about solving for the actual values. We're not analysing the circuit really yet. We're just saying, let's apply Kirchhoff's voltage law around the loop. Are there any questions about that? Good time to ask. Coffee voucher for a question. Yes?
So it doesn't have to any loop, like if the circuit has two loops, would it work for just both loops?
Absolutely. Yep. Any loop in the circuit. Can you pass that back? You reckon? Oh, here's a test. I wonder if it'll get all the way back to him. Yeah, pass that back. Yes, another question. You have to put the signs exactly right. Here it didn't matter. I'm not using Ohm's law. Okay? I've said VR2 is just defined. So when VR2 is just defined for me, I'm not using Ohm's law. When I hit the positive first, it's plus. But it could have been written like this. Could have been written like that in the circuit, and then I would have had to write minus VR1.
What if you are using Ohm's law and you don't have like defined terminals?
We'll show you that in the next thing, all right? So Ohm's law is right with a particular convention. Just drop it now. If the current's flowing in this direction, then V equals IR with pluses at the top terminal. So it's absolutely critical. Ohm's law assumes a convention as well. You have to always remember that resistors would drop voltage. So it's a good point. We'll see it when we actually put currents in the circuit. So here's another example. It says, write KVL for the network. Now it's a bit vague. Well, which loop? I see 3 loops at least that I could do it on. You could say the left loop here, the right loop, the outer loop, and indeed there are other ways in which you can apply Kirchhoff's voltage law in this. So it's a little bit vague. On melts, it says apply it to this left loop here. So I want to apply Kirchhoff's voltage law around that loop. See if you can do it. I'll ask. Well, you can write it down first as I pose the question. $130 responses. Very good to the last one. KVL around the left loop gives. Should be open now. So one very popular answer. It's 90 responses. $115, more than 90% are saying A, and the remaining are saying C. They're in fact the same again, so they're both correct. Let's have a look. Starting at A, I encounter resistor 1 first. Given the sign convention, I get VR1. I then encounter resistor 4. it's plus VR4. I hit this 16 volt source, I hit the negative first, so I write minus 16. I then hit the 24 volt source, hit the negative first. So that is KVL around the left loop. Any questions about it? Basically everybody who responded had that. So I'm going to assume you can do this. Do you want one more practice around the outer loop, or have you got it? Who wants me to do the outer loop, Kirchhoff's voltage law? No one. Excellent. You guys must be pretty good. That's good. So we've done that. You know Kirchhoff's voltage law. You know Kirchhoff's current law. You are all powerful. There's nothing you cannot do now. The first lab involves LEDs, does it? Okay, this is relevant. There's a segment I like called People with Too Much Time on Their Hands, and this involves LEDs and sheep. Some of you may have seen it. Very relevant for the first lab.
We're getting there. We're getting there. Look, that's better. That's more or less enough. Stop there, don't move. Start on the next page. Yes, that's better, that's good. Looking good.
So hopefully that's useful for your upcoming lab. I'm sure it will be. This is really just another application of Kirchhoff's voltage law, but there's just some notation. You have to find VAE and VEC, so we've just got to get that notation under control first. So if I say VBE, it's the voltage between node B and node E. VBE is the voltage between node B and node E, where I take B as positive and E as negative. So in other words, VBE is Vx in this figure there. So that Vx could also be denoted VBE. VBE. Voltage between nodes B and E, where B is the higher voltage reference. The other thing, instead of plus or minus, you could also use an arrow. So I could get rid of the plus and minus and instead do this. So the head of the arrow is like the plus, the tail of the arrow is like the negative. Okay? So they're the two extra little things that you might need to be able to do this. The other thing is we're going to do KVL, not necessarily sticking to the interconnects and elements in a way. You can also do that. I can do Kirchhoff's voltage law around this loop. Even though this bit here is not actually in the circuit. Doesn't matter. Okay. Still just going around a loop, sum the voltages, and they must sum to 0. So let's do that for VAE. Remember, the arrow's up here, so that's plus, and that's minus. So if I start it up here at A and go in this direction, I hit the plus first, so I can write VAE. Then I've got to go across that. It says plus minus 10 volts. I hit the plus first, so I write plus 10. Then I've got to go through the voltage source. I hit the negative first, so it's minus 24 equals 0. Therefore, VAE equals 14 volts. Any questions about that? VAE, the voltage difference between point A and point E, I could put a voltmeter across it and I would get 14 volts in this particular example. Question? Yep. VEA would be minus 14 because the reference would be the other way around. Yep. So it's a sign and a magnitude always with a voltage. All right, you've got to do VEC, find VEC, and that question is open on melts. The third and final melts question for the day. What is VEC? Yep. 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 It does. That's the definition.
So the AE or EA, it's different. It's not.
Okay. So you said the ordering of the. That's a good point. The ordering of the nodes there is. No, it's still the same. It is consistent, isn't it? VEC is the voltage of E. How far E is above C?
Oh,
Yeah? So it is consistent. Yeah. So this is interesting because it's, well, it was more split than it is now. So I'm going to lock that one. 75% say minus 10 volts of 120, 90 out of 120. 25% said plus 10. Let's uncover that then. Let's start here and go around the loop like that. I first hit a plus, so I write 4 volts. I hit another plus, it's plus 6. I hit another plus, it's plus VEC equals 0. Therefore, VEC equals minus 10 volts. So the majority were correct, but a significant number of people had the negative 10. So you just want to think through that example there. What went wrong so that you had plus 10 volts? Got to be careful with the meaning of the arrow, the ordering of the two nodes. Any questions? No. Yeah. Oh, sorry. Reward for asking, not answer. Single loop circuits are nice and easy to analyse. Why are single loop circuits easy to analyse? The same, current's the same, someone yelled out. The same current is in every element. Apply Kirchhoff's current law at any point. I in is I out. I in is I out. The current through every element is the same. That's what makes single loop circuits nice and easy to analyse. You can use Ohm's law with Kirchhoff's voltage law to analyse these circuits like this. There is something called a standard result called a voltage divider, which says I've got a total voltage V, which is going to drop across R1 and R2. How does it split? If R1 is bigger, do you think there's going to be more or less voltage drop across resistor 1? More. So let's just quantify that. That's all the voltage divider does. It's not an extra thing to remember because there is only Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law. Everything is derived from those three things. So we'll come up with a new equation, but remember, it's not anything fundamental. It's just a result of Ohm's law and Kirchhoff's laws. So let us do some voltage division. What does Kirchhoff's voltage law tell me? If I do this, go around the loop that way, it tells me that VR1 plus VR2 minus V equals 0. So the sum of the voltage drops across the resistor is equal to the voltage supplied by the source. VR1 plus VR2 minus V equals 0. Okay, but I can do a little bit more. That equation is going to be called Jamie. So there's Jamie. But what about Ohm's law? What is VR1? How can you write VR1? I times R1 by Ohm's law. Call that equation pasta. And what is VR2? I times R2. And remember, the signs are right for Ohm's law to apply directly. The current is flowing and the drop is plus to minus. It relates to the question earlier. If the current was defined the other way, then I'd have V equals minus IR1 and VR2 equals minus IR2. Ohm's law was defined with signs in mind. So in this case, current flowing into the positive terminal, it is just V equals IR1. This equation is called ice cream. I'm going to now put pasta and ice cream into Jamie. I get V equals IR1 plus IR2, or I outside of R1 plus R2. That equation called Fat Jamie. I put pasta and ice cream into Jamie, I get Fat Jamie. V equals I outside of R1 plus R2. Notice that that's kind of the same equation I would have got if I just had one resistor that was of value R1 plus R2. And many of you will know series combinations of resistors add. That's how you prove that. We've just proved that the series combination of two resistors is equal to their sum. Not something you have to remember, not some magical result, just comes from Ohm's law and Kirchhoff's laws. So if that's true, I know that I is V on R1 plus R2. I can substitute that back into Pastor and Jamie and say that VR1 is R1 on R1 plus R2 times V, and the voltage across resistor 2 is R2 on the sum of R1 and R2 times V. So those two equations there, sometimes it's called just voltage division, tells us how the voltage V splits between R1 and R2, between the voltage drops on the two resistors, just as you told me you would expect. If R1 is bigger than R2, then VR1 is bigger than VR2. More voltage is dropped across the bigger resistor. Any questions? For another coffee voucher? Any? No? No? Oh, yes.
Does it only work when you work in the loop?
That only works when I know that there's a voltage drop across 1, 2, you can extend it to 10 resistors, 100 resistors, 1,000 resistors, but it works in a single loop situation like that. It works anytime I know the voltage across a series combination of resistors, and it tells me how that voltage splits between the two.
So you get a parallel to that, like 200.
If I had parallel, I'd have to reanalyze my circuit using Kirchhoff's laws and Ohm's law again, and what you'll find is you'll be able to find parallel combinations of resistors, what that's equal to. And you get current division, in fact, in it. Oh, sorry. Yep.
How do you know the current in the loop?
How do I know the current all around that loop's the same? Yep. It's like a good question. There's a node. Current in must equal the current out. Where else is the current going to go? Is that okay? So strictly speaking, you could say I'm going to apply Kirchhoff's current law at every point. There's only one thing in, one thing out. But where's all the charge going to go? You'll have to share a coffee with the guy in front, sorry. Get to know each other. I'm out of vouchers. So that is all. Bit of quiet, please. That's all that this slide says. We've just derived that. We've just worked through that. So we have meme competitions with big, like $100 prizes at the end of the year. $100. The things I've seen you do for a coffee voucher, goodness knows what you'll do for $100. You just have to come up with an amazing meme and you could get $100. It has to be yours. There are lots on the internet, but it has to be yours. So I don't know if someone made this up or not, but I say it a lot. I've already said it a lot. All you need is KCL and KVL. And so that was captured by a student in this one. Post them to Facebook, $100 prizes at the end. People's choice and my favourite generally. So well and truly worth participating. Okay, so let's approximate a circuit model. We're generating power somewhere and we're going to send it over a long way over transmission lines to a load, something that's using the power that we're generating. So there's a bit of a model of that. Here's our big high power generator sent over a line, used up in the load. The line is not a perfect conductor. We're not going to say it is a perfect conductor. It in fact has a certain amount of resistance per metre, per kilometre. And in this particular case, we'll assume that the total line voltage is 16 ohms, the load's 183.5 ohms. how much power is sort of wasted in the transmission? That's what this question is trying to get at. How much power is wasted in transmission? So you work out what the power absorbed by the load is and what the power absorbed by the transmission line is. And you'll be able to do that. Now, we've just done voltage division. If you really want to, you could work out what V load is. You could say V load is 400 kilovolts by 183.5 on 183.5 plus 16.5. It's a classic voltage divider. I know there's 400 kVs across a series combination of resistors, so I can use voltage division to work that out. But I already know the current. I'm already given the current here. I don't really need to do that. You could use P equals VI. P equals I squared R. So what is the power absorbed by this load? Well, I squared R, why not just use that? I squared times R, because I already know that I is 2 kiloamps, that's up here, and the resistance is 183.5. So I can plug that in, and you'll get 734 megawatts. The power absorbed by the line is again I squared. That's our load. I squared times R line. The current's the same, but now the resistance is 16.5, and you'll get 66 megawatts if you plug that in. Sanity check. How can I do a sanity check? Any ideas? Quick sanity check on those numbers. See how much the generator is providing, and check that it is the sum of those two, or 800 megawatts. Well, what's 400 kV by 2 Ka? It's 800 megawatts. So as a sanity check, the sum of the powers absorbed by every element is 0, or the power supplied is equal to the sum of the powers absorbed by the line and the load resistance. All right, just wait 1 second. Kirchhoff's voltage law. I'm going to show you why you should never listen to anything I say. How could I induce current in that circuit? Change the magnetic flux through it. So, time varying magnetic field, change it through. Suppose it induces 1 milliamp of current. What's the voltage drop across that 1K resistor? With that sign convention, 1 volt. What about this one? 1 volt. Do Kirchhoff's voltage law around the loop. The sum of the VI equals what? 2. The sum of the voltages around that loop equals 2. Never listen to a word I say. See you tomorrow afternoon. Thank you. Have a think. What's going on?